Method for restructuring the organizational and production structure in a cyber-physical production system. The method of the concept for restructuring the organizational and production structure into a cyber-physical production system provides a structured description of the specific methods and techniques employed to investigate, examine, and analyze the process of fundamentally transforming a conventional manufacturing organization into a digitally integrated production system, thereby establishing a basis for formulating scientifically grounded conclusions with practical applicability. By its nature, the method is realistic. It accurately and adequately reflects the essential characteristics of the restructuring process, the organizational and production structure undergoing transformation, and the resulting cyber-physical production system. Reproducible. Its defined stages enable the restructuring process to be consistently replicated across manufacturing systems of different types, sizes, operating environments, and organizational characteristics. Comprehensible. It is sufficiently clear and transparent, providing a reliable framework for investigating and explaining specific processes, phenomena, and events. Well-founded. Its planned stages and activities are fully aligned with the objectives and research tasks of the concept. Result-oriented. Through its structured sequence of activities, the methodology ensures the achievement of the concept's objectives and the realization of its intended outcomes. The method of the concept for restructuring the organizational and production structure into a cyber-physical production system represents a universal algorithm that can be applied to manufacturing systems of different types, sizes, and organizational characteristics. Its successful application requires only that the specific features and individual characteristics of each manufacturing system be taken into account. The method of the theory of the radical transformation of the organizational and production architecture into a cyber-physical production system consists of a sequence of systematically integrated activities that collectively establish the following algorithm. Determining the resource availability within the business organization. Defining the structural and functional variables of both the physical organizational and production structure and the cyber-physical production system. Selecting the criteria and indicators used to evaluate the optimality of restructuring the organizational and production structure into a cyber-physical production system. Selecting the research methods on which the concept is based. Selecting the tools that support the implementation of the method. Developing the models that provide the analytical and methodological foundation of the concept. The resource availability within the organizational and production structure provides the basis for assessing its long-term synergy potential, which constitutes a fundamental prerequisite for the successful implementation of the restructuring process. On this basis, the concept for restructuring the organizational and production structure into a cyber-physical production system relates the resource capabilities of the manufacturing organization to the following factors. The availability of production resources within the organization. The availability of finished goods that can be converted into financial resources through their sale. The period during which the manufacturing business organization is expected to remain economically viable, profitable, and operationally effective without undertaking the restructuring process towards smart manufacturing. The investment payback period associated with the restructuring process. A fundamental functional distinction between the cyber-physical production system, conventional manufacturing, and its organizational and production structure lies in the capability of the cyber-physical system to self-organize, self-manage, self-adapt, and self-optimize in response to changes in its operating environment. It is this distinctive capability that determines the structural and functional variables requiring fundamental redesign during the radical transformation of the manufacturing organization into an intelligent and autonomous production system. A defining characteristic of this profound transformation is the need to consider both the 5C, architecture of the cyber-physical production system and the two-component architecture of the conventional physical manufacturing system. Based on these architectural frameworks, the structural and functional variables that require radical redesign during the restructuring of the organizational and production structure into a cyber-physical production system are identified. The criteria for evaluating the optimality of restructuring the organizational and production structure into a cyber-physical production system, effectiveness, efficiency, and profitability, together with their corresponding performance indicators, namely operating revenues, operating costs, fixed and variable costs, and operating profit, establish the fundamental dimensions of the optimization model. These criteria and indicators provide the basis for confirming or rejecting the principal hypothesis formulated within the methodology of the concept for the radical transformation of the manufacturing architecture into a smart manufacturing system. The concept seeks to achieve an effective, efficient, and profitable transformation through an optimal restructuring process, thereby ensuring the long-term sustainability of the organization's economic performance, as well as its resource, energy, and environmental competitiveness. For the purposes of the concept for restructuring the organizational and production structure into a cyber-physical production system, three principal categories of research methods are employed. Empirical methods. These are based on empirical evidence obtained through the researcher's direct observation of the studied phenomena and primarily include observation and experimentation. Theoretical methods. These rely on abstract theoretical constructs, including theories, models, methods, methodologies, and conceptual frameworks, where the object of analysis, its processes, and variables are examined indirectly rather than through direct empirical investigation. Mathematical and statistical methods. These involve the processing and analysis of data obtained through surveys and experimental research. They are used to identify, examine, and interpret quantitative relationships among the investigated variables, support the evaluation of experimental results, enhance the reliability of research findings, and provide a basis for theoretical generalizations. Within the theoretical framework of restructuring the architecture and organization of manufacturing into an autonomous digital production system, the principal tools supporting the proposed method include planning, the process of identifying the most appropriate solutions, establishing implementation schedules for specific tasks, and estimating the associated cost. Forecasting, the systematic analysis of the relationships between past and present developments in order to predict future trends based on continuity and patterns of development. Modeling, the development of a comprehensive system of functions representing the principal causal relationships among the elements of the manufacturing organization and between the organization and its external environment. Extrapolation, the extension of established regularities or practical experience to related domains for the purpose of drawing scientific conclusions, as well as a mathematical technique for estimating unknown values of a function beyond the range of observed data. Analogy, the identification of similarities among objects, phenomena, or systems as a basis for formulating scientifically grounded hypotheses and deriving knowledge from the investigation of comparable entities. Regression analysis, a statistical method used to identify stochastic relationships among variables by expressing their dependence through a regression function. Operations research, the systematic analysis of manufacturing operations, including the sequencing of activities, operation times, movement of parts and work pieces, transportation times, machine setup times, technological routing, and production time per unit. Production dispatching, the coordination, monitoring, control, reporting, and regulation of manufacturing activities in time and space, supporting both the management of the transformation process and the achievement of organizational profitability. Control, the continuous comparison of actual performance with planned objectives in order to ensure the effective execution of managerial functions. Roadmaps, strategic planning instruments used to identify risk areas and priority domains requiring continuous monitoring, while documenting performance indicators and development trends. Risk management, the continuous process of identifying, monitoring, assessing, and mitigating risks to ensure the sustainability and reliability of the manufacturing transformation. Balanced Scorecard, BSC, a performance management framework based on the cause and effect relationships among strategic objectives, performance indicators, and the factors required to achieve planned results. Business Process Reengineering, BPR, the fundamental redesign of business processes aimed at achieving significant improvements in the financial and operational performance of the manufacturing business organization. Process and performance management software, software solutions designed to manage, analyze, and optimize organizational resources and manufacturing performance. Brown's Process Measurement Framework, an approach based on the principle that products are manufactured and delivered through a sequence of production operations, recognizing that poorly organized processes are typically characterized by frequent interruptions, high defect rates, and excessive machine setup times. Internet of Things, IoT, a network of interconnected physical objects, including devices, vehicles, buildings, and equipment, equipped with embedded technologies enabling communication with one another and with the external environment. Cloud computing, the delivery of computing services, including servers, storage, databases, networking, software, and analytics through internet-based cloud platforms. Optimization models, analytical tools designed to maximize value creation and improve the efficiency of manufacturing operations. Financial and production performance indicators, measures providing a comprehensive assessment of the long-term economic condition of the manufacturing organization by revealing its development dynamics and performance trends. Simulation, the reproduction of dynamic processes through computational models that realistically represent the structure, processes, and functional areas of the investigated manufacturing system. The Deming cycle, PDCA, a continuous improvement methodology consisting of the stages plan, do, check, act. The Toyota cycle, PDSA, a continuous improvement methodology integrating the stages plan, do, study, act. Six Sigma, DMAIC, a process improvement methodology comprising the phases define, measure, analyze, improve, control. The Ishikawa cause and effect diagram, a quality management tool used to identify and analyze cause and effect relationships within the manufacturing organization. 4M framework, a management tool integrating the key dimensions of man, machine, material, and method. 4P framework, a management approach encompassing the stages of preparation, performance, perfection, and progress. The DuPont Financial Ratio Pyramid, a financial analysis framework that supports managerial decision-making by identifying the organizational areas in which limited financial resources can be invested most effectively. The concept for restructuring the organizational and production structure into a cyber-physical production system should be founded on the integration of the capabilities of mathematical modeling, process modeling, and computer simulation, together with continuous feedback and self-optimization mechanisms. Accordingly, the model of the radical transformation process of the organizational and production structure into a smart manufacturing system should encompass the principal relationships, interdependencies, characteristics, and behavioral patterns of the processes that define both the conventional physical manufacturing system and the cyber-physical production system. The concept for the radical transformation of the manufacturing organization into a smart manufacturing system gives rise to a hybrid model that integrates a broad range of modeling tools, approaches, and techniques. The model for restructuring the organizational and production structure into a cyber-physical production system represents an innovative manufacturing and management framework that simulates the relationships, interactions, and behavior of the manufacturing organization's infrastructure throughout its transformation into a cyber-physical production system.